In this section, we're going to look at second example of a simple harmonic motion, and that's going to be motion of a pendulum. Motion of a pendulum. Now we're going to see in a little bit that the motion of a pendulum is only approximately harmonic when the displacement is very, very small. So a pendulum motion is approximately harmonic, harmonic when the pendulum is displaced by very, very small angular displacement. Is displaced by a small angular displacement. So we're going to see that later, but I just want to make sure that a pendulum is not exactly harmonic, it's only approximate harmonic. Now let's look at the following pendulum. Let's say the pendulum initially is displaced by an angle theta over here. Let's say the length of the pendulum is L. Okay, now the force that's making it move back and forth is of course gravity, right? So you've got this gravity, weight of the object. Let's say this is an object of mass m. Okay, so this is a force that is making it move back and forth. Now we can decompose this force into a component that is balanced by the tension string over here, so it doesn't contribute to the motion. And then we have a component that is tangent to the circular trajectory over here. Okay, so let's call this Fs maybe, and this is the component over here. This component over here would be this force over here. Okay, and this is of course the arc length S over here. So let's call this S, arc length S over here. All right. Now, if this angle is theta over here, you see, this angle is theta over here. This angle is theta, and then these two angles theta. You see these two angles, they're corresponding angles, right? So this is theta. So if this is mg, this component over here, which is this tangential force over here, which is responsible for the motion of the pendulum, is mg sine theta. All right. And the direction of displacement this way, you see, but the force in the opposite direction, so they're negative of each other. So you can say this force over here, Fs, is the negative of mg sine theta. Okay, now as you can see, right now it's not proportional to the angular displacement theta, but for small angles, sine theta is approximately equal to theta. Sine theta is approximately equal to theta. You see, and let's say this is the graph of sine x goes like this. This is the graph of sine x. Okay, sine x as a function of x, and the graph of x goes like this. This is the graph of x. So you see, for small angles, x and sine x are approximately equal. So for small angles, sine theta is approximately equal to theta. So for angles less than 15 degree, if theta is less than 15 degree, we can make this approximation. Okay, so let's say provided theta is less than 15 degrees, we can make this approximation. So with that approximation, now we have this force is the negative of mg times theta. Okay, now this angle theta, remember, if theta is in radians, equals the arc length subtended divided by the radius, which in this case is the length of the pendulum. Okay, so we have theta is equal to arc length subtended by the angle theta divided by the radius, which is the length of the pendulum in this case. Okay, so we have Fs is equal to negative mg, and then this is arc length divided by the length. Okay, so we can write this fs is negative mg over L times s. Okay, so this is the linear displacement, that's arc length. Okay, so we see that this force is proportional to the displacement with this constant of proportionality. Okay, so it follows that the force is proportional and opposite to the displacement. The force is proportional and opposite to the displacement. So what this implies is for small angles, for small angular displacements, typically theta less than 15 degrees, the motion of a pendulum is approximately harmonic. The motion of a pendulum is approximately harmonic. Okay, now we're going to compare this approximately, we're going to compare the general formula for harmonic motion, comparing with the general expression for harmonic motion, negative c times x, where c is force constant. You see, it follows that c, or the force constant, is mg divided by L. Okay, so the force constant for a pendulum is mass times gravity divided by the length of the pendulum. Okay, now if you remember, the angular frequency was given by omega equals the square root of c over m. Okay, so the angular frequency for a pendulum is c, which is mg over L. Okay, mg over L divided by m. It follows that the angular frequency of pendulum is the square root of gravitational acceleration divided by the length. Okay, so the angular frequency of a pendulum is equal to the square root of gravitational acceleration divided by the length of the pendulum. Okay, so of course omega is angular frequency of the pendulum, g is gravitational acceleration, and L is length of the pendulum, and frequency equals, angular frequency equals 2 pi times frequency, omega equals 2 pi f, implies the frequency would be 1 over 2 pi square root of gravitational acceleration divided by the length. Okay, so frequency is number of cycles executed per second. Okay, so that equals 1 over 2 pi times the square root of gravitational acceleration divided by the length. And also period equals 1 over frequency, implies the period is given by 2 pi square root of the length of the pendulum divided by gravitational acceleration. Okay, so these are the formulas for the oscillation properties of a pendulum, that is the period, frequency, and angular frequency. All right, let's look at an example. Let's say a pendulum takes 2 seconds to make one complete revolution on Earth. How long will it take will it take to make one complete revolution on the moon where gravitational acceleration is 1/6 of that on Earth. Okay, so let's use E for Earth, subscript E for Earth, and subscript M for Moon. Okay, so we know gravitational acceleration on Earth is 9.8 meters per second square, and we're told the gravitational acceleration on the moon is 1/6 of the gravitational acceleration on Earth. Okay, now the length of the pendulum is not changing. We're talking about the same pendulum. So the period on Earth is 2 seconds. That is time taken for one complete revolution. So this is the period on Earth. The question is to find the period on the moon. Okay. Now, the period on the moon will be 2 pi the square root of the length divided by gravitational acceleration on the moon, right? And the period on Earth would be 2 pi length divided by gravitational acceleration on Earth. Okay, so let's find the ratio between these two expressions. Let's divide these equations, dividing. So you've got the period on the moon divided by the period on Earth equals the pi will go away. Okay, so you've got square root of L gravitational acceleration on the moon divided by the square root of length divided by gravitational acceleration on Earth. Okay, so as you can see, the lengths will go away, and this equals gravitational acceleration on Earth divided by gravitational acceleration on the moon. Okay, but you see, the ratio between gravitational acceleration on Earth and gravitational acceleration on the moon is 6. Okay, but using this expression over here, the ratio between gravitational acceleration on Earth and gravitational acceleration on the moon is 6. Okay, so the period on the moon divided by the period on Earth is the square root of 6. The square root of 6. So it follows that the period on the moon is square root of 6 times the period on Earth. But the period on Earth is 2 seconds. So it follows that the period on the moon is 2 times root 6 seconds. All right? Okay. The third example of a simple harmonic motion is going to be a physical pendulum. A physical pendulum. This is an object moving about a pivot on the object. Let's say you have this object over here, okay, and let's say make a pivot over here and let it go. It's going to go back and forth. All right, this is an object moving back and forth about a pivot on the object. Okay, about a pivot on the object. All right, so this object, let's say this is the vertical line over here, is being displaced like this, okay, and let's say this angle is theta over here, okay. Now as you remember, for the sake of torque calculations, we can assume that the total weight is concentrated in the center of mass of the object, okay. Suppose this is the center of mass, this point is the center of mass of the object, okay. So you're gonna assume the force of gravity is actually acting on this point over here. So we can assume that the mass, the weight of the object is acting the center of gravity, so this is the force over here, okay. Now let's say this is the position vector of the center of mass with respect to the point rotation, so it's going to be our vector, and let's say this distance over here is d, okay. D is distance between pivot, this one over here is pivot, okay, this is pivot, this is the center of mass, so we extend it by an angle theta and then moves back and forth, all right. So this is distance between pivot and center of mass, and center of mass, okay. So we want to look at the torque responsible for this rotation. You see this object is going to go back and forth like this, it's displaced by a small angle and let go, but the pivot over here is going to move back and forth like this. So the torque is provided by the weight, okay. So the torque is R crossed with the weight, okay. So let's look at the torque. The torque that's producing the motion is the position vector of the center of mass with respect to pivot crossed by the weight, okay, the weight, which is mass times gravity, all right. Now if this distance d over here, you see this angle is theta over here, so if you use this coordinate system over here, y, x, center at the origin over here, okay, so this component is d cosine of theta, this is the angle theta but negative in the negative direction, and then this is d sine of theta in the I direction, okay. So the position vector r is d sine theta in the I direction minus d cosine of theta in the j direction, okay. That's what we have. This is d, this is theta over here, okay. So you've got these components, d cosine of theta in the negative j direction, d sine theta in the I direction, all right. How about the weight? Of course the weight is weight in the negative j direction, okay. So mg, which is the weight, actually equals mg in the negative j direction, okay. That is downward, this is in the negative j direction. So the torque is going as follows, that is r cross mg, that's going to be d sine theta in the I direction minus d cosine of theta in the j direction crossed with mg in the negative j direction, okay. So let's do the cross product. Let me write this over here, cross it with mg in the negative j direction, okay. So let's cross these two. I cross j is k, okay, but it's negative, it's going to be the negative k direction, okay. So you've got this equals mg d sine theta in the negative k direction, okay. And then of course this one, j cross j is 0, so the torque is going by this expression. So you've got torque is negative mg d sine theta in the k direction, all right. Now the torque also equals moment of inertia about the axis through the pivot, you see about the axis, which times angular acceleration, okay. But angular acceleration is the second derivative of angular displacement with respect to time. Okay, so this is going to be in the k direction. Okay, in the k direction. All right, so you equate these two expressions, we have the following: moment of inertia times the second derivative of the angular position with respect to time equals negative m g d sine theta. Okay, now we're going to make an approximation. It's harmonic only when the angular displacement is very small. Okay, so for very small theta, very small theta, typical theta less than 15 degree, we can make the following approximation: sine of theta is approximately equal to theta. Okay, so we can make the following approximation: the moment of inertia times the second derivative of the angular displacement is negative m g d times theta. Okay, now let's take the other side. We get I d squared theta dt squared plus m g d theta equals 0. Okay, let's make sure the coefficient of this one is 1 by dividing by the moment of inertia. So you've got d squared theta by dt squared plus m g d divided by the moment of inertia times theta equals 0. Okay, but if you remember, this is an equation of a simple harmonic motion. Okay, comparing with the following: d squared x dt squared plus omega naught squared x equals 0. It follows that this is a simple harmonic motion with this being equal to the square of the angular frequency. So this implies the physical pendulum is approximately harmonic for small angular displacements with omega naught squared equals m g d over moment of inertia. Okay, so the angular frequency for a physical pendulum is going by the following formula. It is equal to the square root of m g d divided by the moment of inertia. So this is the angular frequency of a physical pendulum. Okay, so in this formula, m is mass of the pendulum, of the physical pendulum. Okay, d is distance between pivot and center of mass. Distance between pivot and center of mass. Okay, and I is moment of inertia about an axis through the pivot. Okay, all right, and of course omega naught equals 2 pi f naught, so we can say f naught equals 1 over 2 pi square root of m g d divided by the moment of inertia. Okay, this is the frequency of a physical pendulum, and the period is 1 over the frequency, so you've got the period is given by 2 pi square root of moment of inertia divided by mgd. Okay, so these are the formulas for the oscillation properties of a physical pendulum. All right, let's look at an example. Let's say we have a physical pendulum that is a rod. Let's say we have this rod over here. Okay, so let's say this is a pivot over here. So let's say this is the center of mass over here. Okay, the center of mass over here. And then of course this physical pendulum, this is the edge of the rod, and then of course we'll go back and forth like this. Okay, and so let's say this is L, this is L over here. All right, and we want to obtain a formula for the angular frequency. This is the length, and let's say the mass is m. Okay, for this pendulum. So the question is obtain an expression for its, let's say, angular frequency. All right, so that is, we want to find this one. Okay, but we just saw that this is the square root of mgd divided by the moment of inertia. So in this case, you see, let's say this is uniform rod, so the center of mass would be located at the center of the rod if it's uniform, right? So that means d, the distance center of mass, and the pivot is L over 2. All right, now we just have to calculate the moment of inertia. Now the moment of inertia over here can be related with moment of inertia passing through the center of mass. Okay, so we can use the following formula. Moment of inertia equals ICM plus m d squared. Okay, d squared. ICM for a rod, if you remember, is m L squared divided by 12. Okay, that is moment of inertia for a rod about an axis passing through the center of mass perpendicularly. You can find this in textbooks. So with that, we have the following formula for moment of inertia: ml squared over 12 for the moment of inertia about an axis passing through the center of mass perpendicularly, and then you've got m, d is L over 2, the distance between the center of mass and the pivot, L over 2 squared. All right, so we've got this is moment of inertia equals m L squared over 12 plus m L squared over 4, m L squared over 4. Okay, so we can factor out m L squared, and then this is 1 over 12 plus 3 over 12. Okay, that is m L squared times 4 over 12, or 1/3. This equals 1/3 m L squared. Okay, so this is moment of inertia of the rod about this point over here. All right, so that's it. So now we just use the formula. We've got omega naught equals square root of m gravitational acceleration times d divided by moment of inertia. All right, so we have this equals square root of m g, d is L over 2, and the moment of inertia is 1/3 m L squared. All right, so the mass cancels out. Okay, and then of course one of these L's will cancel out, so you've got omega naught equals the square root of gravitational acceleration divided by well, the 3 will go up, so it's going to be 3 over 2. 3 over 2L. Okay, so this will be the formula for the angular frequency of a rod. Right. And then we're going to look at a third example. I think it's a fourth example. Our fourth example is going to be torsional pendulum. Torsional pendulum. This is the case where you twist a wire. Let's say I have a wire over here. Let's say you twist the wire and let it go, then it's going to rotate back and forth. If you twist the wire, let it go, then the object will rotate back and forth. Okay. This is a case where a wire is twisted, where a wire is twisted and let go. Okay, you twist the wire and let it go, and then it's going to rotate back and forth. Okay, now the torque is proportional to the twisting angle. Okay, the torque is proportional to the twisting angle. So we have torque is negative k theta, where k is called the torsional constant. This is the Greek letter kappa, where kappa is called the torsional constant, and theta is the twisting angle. Okay, but if you remember, torque is moment of inertia times angular acceleration, or moment of inertia times the second derivative of the angular displacement or twisting angle with respect to time. Okay, so that gives us moment of inertia d squared theta by dt squared is equal to negative torsional constant times the deflection angle or twisting angle in this case. So we have a second derivative of angular displacement plus torsional constant theta equals 0. And then let's make the coefficient of this one 1. So you've got d squared theta dt squared plus kappa over moment of inertia times theta equals 0. So this is the equation that governs the motion of this object, okay, which is equation of a simple harmonic motion. This is equation of a simple harmonic motion with omega naught squared equals torsional constant divided by moment of inertia. Okay, so this is simple harmonic motion, where this is the square of the natural angular frequency. Okay, so this implies omega naught is square root of torsional constant divided by the moment of inertia of the object, and of course f naught would be 1 over 2 pi square root of torsional constant divided by moment of inertia, and the period would be 2 pi square root of moment of inertia divided by torsional constant. Okay, so these are the formulas for a torsional pendulum, right? All right, so let's look at an example. Let's say we have the following. Let's say this this disk of mass m and let's say radius r is suspended by means of a wire. Okay, a disk of mass m and radius r is suspended by a wire at its center, okay. It is twisted, the wire is twisted and let go. The wire is twisted and let go, okay. Now if the torsional constant of the wire is kappa, obtain an expression for the angular frequency of the motion. For the angular frequency of the motion. Okay, so we just need to obtain the moment inertia. So this is the formula for the angular frequency, square root of torsional constant divided by the moment inertia. Now this is moment inertia about an axis passing through the center of mass of the disk. Okay, so it's going back and forth this way, rotating back and forth this way, and we know that this I is ICM because the axis of rotation is passing through the center of mass of the disk, and that is 1/2 m r squared. Okay, so the angular frequency is square root of kappa divided by 1/2 m r squared, or the natural frequency for this motion is 2 times torsional constant divided by the mass of the disk divided by the square of the radius. So this would be an expression for the angular frequency of this motion. All right, now we're going to look at dampened motion. Dampened motion is a motion where there is an additional resistive force proportional to the velocity in addition to the restoring force. Okay, dampened motion is a motion where there is a resistive force proportional to the velocity in addition to the restoring force, So in this case we have two forces. So the net force is restoring force. This is of course the force proportional to the displacement, the force we've been talking about, plus resistive force, which is proportional to the speed. Okay, we have these two forces involved. All right, the restoring force proportional to the displacement, and then you've got a resistive force. This is usually air resistance, water resistance, and so on. So examples of resistive forces are air resistance and water resistance and water resistance. Okay, so F net in this case is resistive. It opposes the velocity. That's what we call resistive. So in this case, the F net is negative kx minus bv. Okay, of course k is the well, I would rather use c for this one. This is for a spring, but let's make it general. So let me use the first constant c over here instead of k. K is particularly for a spring. So we have a c over here, negative cx minus bv. All right, but this one, as we know from Newton's second law, is second derivative of position with respect to time. Okay, so we've got the following formula: mass times acceleration equals negative cx minus bv. Okay, take the other side. So you've got m, second derivative of position with respect to time, plus the restoring force proportional to the displacement, plus the resistive force proportional to the velocity, equals 0. Let's divide by m. First, let me put this one. This is dx by dt. Okay, the speed is dx by dt. So this equation becomes m d squared x by dt squared plus the constant proportions for the resistive force dx by dt. Okay, and then plus cx equals 0. Now let's make the coefficients of second derivative 1 dividing by m. So you've got the following equation: dt squared plus b over m times the velocity plus the restoring force cx equals 0. So this is the equation governing the case where you have both a restoring force and a resistive force. Oh, I didn't divide by m. Okay, now you remember this one was the natural frequency omega naught. Okay, if b is 0, this will be the frequency. Okay, so we're going to say c over m equals omega naught squared. This is angular frequency when there is no resistive force, when b equals 0. Okay, and then we're going to say let b over m equals 2 beta, where beta is called the damping constant. Is called the damping constant. Okay, now with the substitutions we have the following equation: the second derivative of position plus 2 beta times the velocity plus the natural frequency squared times x equals 0. Okay, so this is the equation governing the motion for the case where we have both the restoring force proportional to the displacement and the resistive force proportional to velocity. Okay, so this is a second order differential equation with constant coefficients. Okay, so this is a second order differential equation with constant coefficients. Now the solution of a second order differential equation is two-dimensional. Its solution is two-dimensional. Okay, which means if you can find any two linearly independent solutions, then the general solution is the linear combination of the solutions, which means if we can find any two linearly independent solutions, linearly independent solutions, the general solution is a linear combination of those solutions, a linear combination of those solutions. Okay, that is, this means, for example, if f1 and f2 are solutions, are linearly independent solutions, linearly independent solutions, then the general solution is let's say f equals c1 f1 plus c2 f2, where c1 and c2 are arbitrary constants to be determined from initial conditions, Okay, so now what we have to do is we have to find two linearly independent solutions of this differential equation. Okay, now when we solve equations like this, we try a solution in the form of e to the power of rt, because the derivative is the second derivative of an exponential is proportional to the function itself. The first derivative of an exponential is proportional to the function itself, and so on. So we're going to try a solution of the form. Okay, let's try a solution in the form of e to the power of rt. Okay, we're choosing this function because we know that the derivative and second derivative of this function are proportional to the function itself. Okay, so with x of t equals ert, let's see what conditions have to be satisfied for this to be a solution. Let's put in the differential equations. So you've got the second derivative with respect to time of ert plus 2 beta, the first derivative of ert plus omega naught squared of ert equals 0. Okay, so the second derivative of this one is r squared ert. Okay, the first derivative of this one is 2 beta, and then you've got r, and then you've got ert. Okay, then you've got plus omega naught squared ert. Okay, so we can divide this equation by ert. You see, this implies r squared plus 2 beta r plus omega naught squared equals 0. Okay, so what this means is ert is the solution provided this condition is satisfied. Okay, all right, this implies ert is a solution provided r satisfies this quadratic equation in R. Okay, so if R satisfies this equation, then we have a solution. Okay, now A quadratic equation can have two solutions or one solution. It's a perfect square. Okay, so we're gonna have three different cases. Well, first let me write the general solution of this equation, of this quadratic equation. It is r equals, first let me write the form of quadratic equation. You've got x squared plus let's say a bx plus equals 0. This implies x equals negative b plus or minus square root of b squared minus 4ac divided by 2a. Okay, therefore this implies in this case what we have is our b is 2 beta. Okay, our c is 1 and no, our a is 1, and our maybe just let me write the, I don't want to compute this b with the coefficient of the velocity, so let me just write this equation, write the solution. So this is our equation, plus 2 beta r plus omega naught squared equals 0. So the solution for this one is we have two solutions, plus or minus equals negative b, which is negative 2 beta, plus or minus square root of b squared, which is 2 beta, okay, 2 beta squared, minus 4 times a is 1, and this one is omega naught squared, divided by 2 times 1. Okay, the coefficient of r squared is 1. So this implies we've got two possible solutions, r plus minus equals, you divide this by 2, you get negative beta, and then plus or minus. Now when you put the 2 inside the square root, it's going to be 4, so this goes away, so you've got beta squared minus omega naught squared. Okay, so these are the two possible solutions. Okay, so there are two possible solutions. There are two possible solutions. Of course, if beta squared minus omega squared is not equal to 0. Okay, so you've got r plus would be negative beta plus square root of beta squared minus omega squared, and r minus would be negative beta minus square root of beta squared omega squared. Okay, and there is only one solution, and there is only one solution if beta squared minus omega squared equals 0. Okay, now so there are three different kind of solutions depending on this expression over here. Okay, if this is positive, we have two real number solutions. If this is negative, you have imaginary solutions, and if this is 0, then we have only one solution. Okay, so because of that, we have three different cases. Okay, there are three different kinds of solutions. There are three different kinds of solutions depending on whether beta squared minus omega squared is positive, negative, or 0. Okay, so we're going to look at these three different cases. Okay, the first one is called the underdamped case. It occurs when beta squared minus omega squared is negative. So case 1, underdamped oscillation. Underdamped oscillation. Okay, this occurs when beta squared minus omega squared is negative. This occurs when beta squared minus omega squared is less than 0. Okay, so first let me remember these two solutions. The two roots are, in this case, we have r plus equals negative beta plus square root of beta squared minus omega squared, and then r minus equals negative beta plus square root of minus square root of beta squared minus omega squared. But what does this equal to? Okay, this expression is now negative, okay, because it's less than 0. Now square root of beta squared minus omega squared equals square root of negative 1 times omega squared minus beta squared, okay? But square root of negative 1 is the complex number I, so this equals I omega squared minus beta squared, okay? Now let's say let omega squared minus beta squared equals omega squared, okay? Or this is the actual frequency where omega is the actual frequency. See, omega naught is the frequency for the case where the damping constant is 0, but this is going to be the actual frequency of the underdamped oscillation. Okay, so with that we have the following solutions, or you can say omega equals square root of omega squared minus beta squared. So with that, our two solutions are r plus equals negative beta plus omega, and r minus equals negative beta, oh there is an I over here, I'm sorry, plus I omega. All right, so the general solution, therefore the general solution is x of t, arbitrary constant c1, and then e r plus, that's negative beta plus omega I times t, and then plus arbitrary constant c, and then we've got e negative beta plus I omega t. All right, so this is the general solution where c1 and c2 are arbitrary constants. All right, now we can factor out the negative beta with plus 1 is minus over here. Okay, so you can factor out the e negative beta, so you've got e negative beta t, this equals c1 e omega I plus c2 e negative omega I. Okay, for this time over here, sorry, time over here. Okay, let's expand this. If you remember the formula, I theta equals cosine of theta plus I sine theta. Okay, so you guys using the formula I theta equals cosine theta plus I sine theta, we can write this as follows: x of t is e negative beta t, and then you've got, this is cosine omega t, there is c1 over here, maybe let's put c1 over here. Okay, c1 cosine omega t plus I sine omega t, and then plus you've got IC2, and then you've got cosine of negative omega t plus I sine of negative omega t. Okay, now if you put the cosines together and the sines together, there's a big bracket over here. Let me write this over here. This is very clear. So we've got, let me write a big line over here. So x of t equals e, you get beta t. Okay, so the first one is c1. That is, if you expand this one over here, you get cosine omega t plus I sine omega t. Okay, and then another one, you got c2 constant over here. You've got cosine of negative omega t plus I sine of negative omega t. Okay, and then we've got a big bracket over here. All right, now we can combine cosines with cosines and sine sines. Now you see cosine of negative omega t is equal to cosine of omega t because cosine is an even function. Okay, so it's just c1 plus c2 times cosine of omega t. So let's simplify this. So we've got x of t equals the damping constant e negative beta t, and then you've got, we can factor out cosine of omega t first, and that gives us c1 plus c2. Okay, and then we're going to factor out sine omega t. Okay, now remember sine is an odd function, so the negative will come out over here. So we have I c1, this is I c1 minus I c2. Okay, all right, so these are just arbitrary constants. So let's say let c1 plus c2 equals maybe c1 prime, and IC1 minus IC2 equals C2 prime, the arbitrary constants. So you've got the following: x of t equals e negative beta t, and then you've got C1 prime cosine of omega t plus C2 prime sine omega t. All right, now we're going to transform this into the constants a and phi. Let's transform c1 prime and c2 prime to a and phi using the equations. The equations c1 prime equals a cosine of phi, c2 prime equals a the sine of phi. Okay, so with that we have x of t equals e negative beta t, and then c1 is a cosine of phi, a cosine of phi times cosine of omega t, and then the other one will be a sine phi sine omega t. Okay, now you see this is simply equal to cosine of omega t minus phi using the formula for the sine of the cosine of differences. So this implies x of t is given by e negative beta t, and then we have a cosine omega t minus phi. Okay, so this is the general solution of an underdamped motion. Let me write over here again. You've got x of t equals e negative beta t times, I'll put a over here, a cosine of omega t minus phi. This is general solution of underdamped oscillation. This is general solution of an underdamped motion, which means beta square minus omega square is less than 0, with arbitrary constants a arbitrary constants a and phi. Constants a and phi. Okay. Now this is the meaning of this. So this solution is oscillatory, damped by the exponential e negative beta t. Okay. So this solution is a damped oscillatory motion. This motion is an oscillatory motion damped by e negative beta t. Okay, so this one we have this one. This is cosine of omega t minus phi, and then you multiply it by another function that goes to 0 like this is e negative beta t. This gives you a solution something like this. You start here and it keeps decreasing, it goes like this. Okay, so this is the damped, underdamped motion, underdamped oscillatory motion. This is like this is x of t, this is time. Okay, this is underdamped oscillatory motion, underdamped oscillatory motion. Eventually it goes to 0. Okay, the second type of motion is overdamped motion. Overdamped motion. Okay, this occurs when this one beta squared minus omega squared is greater than 0. All right, so there are two solutions to the characteristic equation. So in this case, the two linear independent solutions are the two linearly independent solutions are, you've got e r minus t, which is e negative beta minus square root of beta squared minus omega squared times t, and the other solution is r plus t equals e negative beta plus square root of beta squared minus omega squared. Okay, so these are our two independent solutions. Therefore the general solution is, therefore the general solution of overdamped oscillatory motion is the linear combination of these solutions. So you can say x of t equals arbitrary constant c1 e negative beta minus square root of beta squared minus omega squared t plus another arbitrary constant e negative beta plus square root of beta squared minus omega squared t. Okay, so this is the general solution of overdamped motion, where c1 and c2 are arbitrary constants, to be determined from initial conditions, initial conditions. Okay, now this looks like the following. This is x of t. This is not oscillatory, but it will eventually go to 0. So we'll go like this, eventually go to 0 like this. Okay, You see we've got E negative beta T, E negative beta in this case, so that eventually will go to 0. You can see this negative value is bigger than this one, this negative value, so generally it will go to 0 eventually. All right. And then we have critically damped motion. The third one is, this third solution is critically damped motion. Critically damped motion. This occurs when beta squared minus omega squared is equal to 0. So in this case, we have only one solution. In this case, there is only one solution. There is only one solution, okay, which is E negative beta T, okay? If this is 0, then we have only this solution, E negative beta T, all right? But we need two solutions, okay? But it can be shown that by direct substitution, direct substitution, if E negative beta T is a solution, then also T E negative beta T is a solution, okay? So the general solution can be expressed as a linear combination of these two solutions, okay? Therefore, the general solution can be written as x of t is C E negative beta t plus C2 T E negative beta t, okay? So we can factor out E negative beta, so we can write this equals E negative beta t, and then you get C1 plus C2 t. So this is the general solution for a critical damped motion, where C1 and C2 are arbitrary constants and C2 are arbitrary constants to be determined from initial conditions. Initial conditions. Okay. Now, as you can see, this is a damped motion. You get a term increasing with t, but this one eventually will go to 0 faster than this one. So the graph will look something like this. This is x of t. The particle eventually go to 0. Okay. The difference between over-damped and critical damped is the particle goes to 0. The particle goes to 0 faster for critical damped than over-damped. Okay. An over-damped oscillation takes longer to go to 0 than a critically damped motion. Okay. So the difference between critically damped and over-damped is that critically damped goes to 0 faster then over damped, then over damped. Okay, so let's put three of them together now. Oscillatory will go like this, eventually it will go to 0. Okay, so this one is under damped, oscillatory motion. Over damped will go to 0 slowly. This is over damped, and then we have critical damped that goes to 0 faster. Okay, so this one is critically damped, So these are the three kinds of motions we have for damped motion. We have under damped motion when the discriminant is negative. We have over damped motion when the discriminant is positive, and then we have critical damped when the discriminant is 0.